太好吃了，实在是。
这些都知道。
太高兴了，超完这个。
高一的时候，以前高二的时候，我坐我前面那个女生也是高。然后我
94年的也太大了。没有，他是9年。
我发现我那个驾照是他妈的生日前一天就能骑回来。
拿到驾照了。
不是实体版的驾照，是概念版。
然后现在骑过拿到了。
那就要记。
那也不是要看嘛。那你还是那你给他还是那个20岁以下，是就是4月份手头过来。
没有，
这4月1号，4月10号。
4月1号。我们1个月之后啊，天哪！
1个月一个作业。
现在你还往1.7啊。
就是2倍几。
技术我还是不知道，我来上课可说一说。
就这样让我们一起骑。
才一个月。
我觉得，不想要让
Okay, I guess we'll get started. Can you hear me okay? So homework 2 going out, homework 1 today. I left room here for the break. Be back for 1. There'll be one more homework after that. And then the midterm exam. We're in March. ，similar to homework 1, but adapted to CMOS. Okay, our current topic of conversation is charging and discharging of capacitive loads. And we will once again resort to just analyzing what happens with an inverter. Clearly, there are extensions of this to driving capacitive loads with more complicated beats, and you must adapt what I'm telling you about with the inverter to more complex gate structures. Anyway, here's an inverter. In simplified symbols we discussed earlier. And there's an output. And we're going to apply an abrupt input, so like a step function. 0 to basically go from 0 volts to VDD. We apply it to both gates. shutting this one off and of course turning this one on, you will be progressing through the stat region, during which time it's kind of like having a short circuit. The two that are sort of partially on. There's a slug current that's going to run right through. That's the switching noise that happens very quickly. We move very quickly to the other side of the VTC. And we're going to ignore the amount of time it takes to go through the VTC from one side to the other, which is a pretty good approximation for heavily loaded gates, in which case the majority of the delay is going to be determined by the characteristics of the field effect transistor current capability, what its current carrying capability is, and the capacitance value we can close. So the V out is essentially across the capacitor, and also of course VDS for the entire device. VDS for the entire device is going to depend on the amount of current that's flowing, and so as a result, we'll be charging and discharging the capacitors. When we do this, it's discharge capacitors chosen to analyze. And we basically pull the charge off the load capacitor to the ground. Incidentally, this is where a lot of energy disappears. People like CMOS because they think it's low energy. But what we're doing is we're dealing with tidal flows of energy in the form of charge storage, like down to this conductor. And then we dump it to ground. And guess what? When we do that, the charge produces zero voltage, and the energy has to go someplace. Where do you think the energy goes? Heat. And the transistor. And you have a really tiny transistor, that heat's going to come out of a really tiny area. And there's an Ohm's law for heat. It says the tinier the cross-sectional area, the more heat is. This is becoming increasingly a problem for scaling, especially if it turns out you can't really scale the voltage. This energy that's stored out here is, of course, going to be 1/10 of the voltage squared times the capacitance. So that's fixed pretty much by this load capacitance, which is a stunning result. You can see it already without having to get, even though the heat's coming out of this device, this is the device that's determining the heat dissipation. Because once you fully charge it, that's the amount of energy that's there, and it's all going to be dissipated as heat. And the resistor will be dumped up in this current. So we're never actually doing anything with the resistors where we compute heat for CMOS. It's all about this guy over here. Believe me, there's a lot of experts trying to figure out how to get that down. The process of doing it, there's a little sneaky guy that's starting to show up here to the wire. Resistor here. We're going to ignore that resistance in this calculation. So any C-cell has an initial voltage V out, which is called VC, which is initially going to be maybe VDD, or possibly not fully VDD, even though this we're assuming is VDD, and it will be really nice if that's VDD. We know that we're going to get something like a charging or discharging behavior, and an RC charging and discharging behavior never gets to its destination. It's just exponentially approaching. So it never really gets to be. I'm just assuming that from the moment of discussion, and then we'll refine that a little bit. Anyway, as we turn this transistor on, whatever charge is stored in that capacitor will discharge this capacitor voltage, will decline from its initial value toward zero. And if we wait long enough, we will get all the way to zero. But again, this is an exponential charging and discharging behavior. And so it never does quite get all the way there. So we have to be satisfied with almost getting there. We'll talk about that in a second. Anyway, anyway, the circuit that we're really talking about during discharge, since the top one is off, is just this pair, in which case the Kirchhoff voltage equation, current equation, it's stating that conservation of current, or charge rather, would look something like this, where the IDSN is defined in this direction. And to get this guy over here to be have its current going in the same direction, would make the positive to negative side up here. So they're on opposite sides of the equation. Usually, bring it over here. You don't really have to worry about a negative sign, but the current's actually leaving the positive terminal here and entering it over here. So this is the Kirchhoff current equation. Very simple. The only trouble is that this guy over here is a nonlinear resistor of sorts, nonlinear device. And as I said last time, we're going to assume that we zip through the transition, turning this guy off to that one on very quickly compared to whatever the charge and discharge time is with this lower capacitance.
Do you remember about this?
Yeah. And so if we look at the characteristic for the N-type device, which is something like this, prior to having this step applied, it would be cut off down here. The capacitor would have charged all the way to, well, let's say VDD, that's not going to quite get there either. So it starts at VDD. And then we abruptly change the voltage and we snap from this characteristic up to this one. So this is the one where VDSN is equal to VDD. And it happens so quickly that essentially the capacitor is like an inert element, an inertial element that doesn't have its voltage, can't change properly. And so it's sort of stuck at that voltage. Then as soon as the switch is on, you're going to begin to drain current off the capacitor. And the voltage at the output, which is also UDS from the N-type device, is going to decline. However, there is a point at which the nature in which this draining current will switch over. This was a saturation area, so of course it's cut off. And then it will merge into an active region. So we got, and the transition is here. We all know what that famous equation is. That's the normal VDS in minus the threshold, and it's equal to VDSN. That's that voltage there. And if we charge up all the way to VDD, this VDSN would be in fact decreased. Of course, even this one is probably not going to charge all the way up. But we're doing an artificial math problem. I want to keep the math simple so you can learn something about how the circuit works. In the real world, we usually rely on simulation, which is why when I leave next week to go to Washington on the 9th, the following Friday, we'll have another tutorial. And this is where the simulation engine is. So you can simulate these devices and get something which is a little more realistic. But it's hard to look at that and actually understand what's going on. So we use simple mathematical structures to exposit them in the lecture. Anyway, so this is going to charge from discharge from VDD down to VDD minus the threshold, which means this might be 2/10 of a volt. Maybe 1 volt to 5 volt here that we're doing with our kit. And it's roughly factor 5 down from what this is. In more modern structures, we're unable to make the threshold go down, and yet we're trying to keep on the voltage to make it go down. And so we're not spending that much time in saturation up here, as much as we are in the current kit that we're working with. So that's the new status for the field. And the transition was a lot earlier than when we went to FinFET. FinFET has more to do with leakage problems. Turn the device off. So, all right. let's analyze this first section here. We'll take a certain amount of time, and I'll call that tau fall 1. Tau F1. And the remaining descent down to 0 will be a tau F2. And we'll calculate tau F1 first, which is the saturation part of the characteristic. Okay. So IDS in the saturation region is going to be our beta n over 2 times, and the assumed or presumed input voltage is going to be a full VDV. Probably isn't that in the real world, but we make it so for the purpose of analysis. So that's our it's our equation for IDS sat, which means our differential equation is now this. And it's going to be that till we get to VDS in equals V out equals VGSN, which is also presumed now to be exactly VDV minus V threshold in, or VDV minus V threshold in. So again, the assumption here on the input is perfect. We use a signal generator or something to pull it in here. So we move this to the other side of the equation. It'll be having a minus sign in front of it. But then I'm going to flip some of the integration order around so that it winds up becoming positive. And what I'm going to do is, instead of what I'm going to do is I'm now going to adapt the notion that we're only going to be starting with the initial voltage and the output of 0.9 VDV, 90% of VDV. So there's a little change here. And, so we're going to start out at 0.9 VDV. And this is going to be go through the transition point. So if this is 20% VDD, this is 0.9 VDD, and this would be more like 0.8 VDD. If this is 20%, okay, then C sub L dV out divided by beta n over 2 VDD minus V threshold n all squared is going to be equal to integral from T1 to T2, where the T2 equals to tau fall 1. This is in the sat region. Just as a comment, if we look at this 0.9 VDD, and you know this is, the denominator is not a function of V0, so it's just going to get shoved out from the unit. We're really going to be integrating the V0 between the limits of 0.9 VDD and minus VDD minus threshold, which is plus threshold n, which is V threshold n minus 0.1 VDD. Now that 0.1 has to do with 90% charging model for not going all the way to the end, because you have to wait around for infinity for that to actually happen. So if we do this integral and integrate this d0, stick this in, what do we get? We can bring all this stuff out in front. And there's a 2 in the denominator here, so we'll just move that up to the top. And this tau fall 1 would then be equal to 2 times C sub L divided by beta n. And this is all constants down here. Times this 0.9 VDD minus VDD plus the threshold for the n. Okay. And so after moving things around, this is 2 C sub L, U threshold N minus 0.1 VD, all divided by beta N times VDD minus V threshold N all squared. Now, something that is done in the book and in several books is to take this equation and divide it all by VDD on the top and the bottom. So divide by VDD, top and bottom. The VDD will come out of here, okay, and it'll be squared, but then there'll be another one come out here and cancel. So when we do that, tau f is equal to 2 C sub L divided by beta n times VDD times, okay, now I'm going to make this is a parameter for the V threshold n. I'll write it as 3n divided by VDD. I'm just going to define that parameter. The ratio of the threshold voltage to the supply voltage. And if I do that and divide by VDD over here, I'm going to get 1 minus n squared. I put 1 in here. And then there'll be 1 up in here. This is going to be n minus 0.1. And I'll divide by the other one over here, 1 minus n. And the reason for grouping it that way is we've only just analyzed TF1, the first part of it. And there'll be another piece for the other segment. But I'll share some things already that you can see in common with this. Now, the first thing that you'll see, of course, is a really obvious one. If the load capacitance is big, well, the flow time is going to be long, all right? So one of your goals in design is to try to minimize capacitance as much as possible. And people relied on scaling for most of the history of CMOS to do that for them. Shorter wires, we get less capacitance, but then the wires turn into resistors, and so that tends to sort of diminish. But right now, there's no resistance in this circuit other than what's associated with the switch itself. And so bigger capacitive load, the longer decay time. What else can we observe? It's divided by beta n. Okay, what is beta n? Remember, so the formulas that we read earlier in class, which is UN Cox times width length in the n-type device. So if we would like to speed things up and make things go faster, we should try to make the width bigger than the length. Well, we've been doing a certain amount of that to just to balance pull up and pull down. Here's a case where we might be doing the same scaling factor to pull up and pull down and make it even bigger, wider, than we would have tried to do in the minimalist case, just trying to make the TC capacity we need to be able to do. And it says the wider I make the driver, but in this case the sink, the faster I can discharge the charge. So it's like the wider I make this, if I wanted to think of this as a kind of a quasi-resistor, then the resistance in the circuit is going down. Make it wider, it's less resistance. Same thing with the resistor. Okay, and that'll speed things up. And there's a few other things you can think about. You can try to make the mobility get better. That's where all our hobbyists have been pouring liquid nitrogen on their microprocessor chips and their memories out in Trump Tower or something. And finding their Celerons are running at what? As I go, like 8.9 gigahertz. Because all the wire discharging and charging has been sped up. This beta is improving. The wire is totally resistanceless at that point. It goes down by next to factor 10 or 10. So we could try to fiddle with mobility by going down in temperature. How about Cox? Now, there was a period in the shrinking process where we were not going anywhere because we couldn't shrink the oxide thickness anymore. It was as thin as it was going to get. We need to make it back bigger if we want to get bigger yields. The only way to do that would be to find a higher dielectric constant material. And there are plenty of them around. You can find lots of things that have dielectric constants normalized to epsilon naught of 20 or 30. Trouble is, you could make a thicker oxide then, so maybe you could avoid some yield issues. Trouble is, it's not very uniform. It's not like silicon dioxide. You have to make a wafer of 18 inches in diameter. Absolute pristine oxide with a thin oxide. And this is common even for the Josephson junction technology. But you've got to have this enormous uniformity. Very hard to do for anything other than silicon dioxide. But they did find something. It was silicon hafnium oxynitride, which had maybe a dielectric constant 2 or 3 times larger than silicon dioxide. So this could be made bigger without having to shrink the thickness of the device. And so that would help with the charging and discharging mechanism. We wanted to use a large dielectric constant for the thin oxide. Of course, to keep the capacitance down, we wanted a low dielectric constant for that capacitance. People were playing around with polymers, even some that had fluorine in them, like Teflon or silvery, had enormously low dielectric constants of maybe under 2 for building the wire. And people had actually used some fluorine-containing dielectrics for the Josephson junction work. But it's not like it hadn't been thought about. It was just kind of like a seesaw. You wanted to make this capacitance big and the load capacitance small. You can possibly do that. Okay, so here's the killer. To make TF1 low, it suggests we should make VDD high. But the energy stored on the final capacitance would be higher by the square of VDD big. And that used to be the rule. If you wanted to have a high frequency microprocessor, you had to run towards the high end of the VDD. And most of the higher clock rate processors that IBM makes now, the T196 at 5.5 gigahertz without using liquid nitrogen, you do have to have maybe 1.2 volts. So it's on the high end of VDD for today's types of transistors. And they try to make this as big as they can to pull this ratio down. And so that would make things run faster. Because the currents would then be faster to take the charge off, even though the energy stored is important to square of VDD. And then the only other knob that you've got is this 1 minus n thing here. And this whole factor that's sitting in there. I guess the other observation, which I will do with a little red pen, is that even though this is a highly nonlinear circuit at this point, it does look like there's some capacitor here multiplying something else. And that something else could be an R equivalent. For all that nonlinearity. We haven't got all of this. There's more to this story because we're not looking at how one, but you can already tell a lot just looking at this piece. It looks like an RC product. This is the R. The stuff that I circled red. But it's not a resistor. It just kind of plays like it. It's something that limits current, and that's what resistors do. This is a nonlinear device, and various people will talk about transient inductance and other things. We'll explain it away, but basically that's what it is. So we've got only part of this story. But it's already very revealing. It tells you some things about how to get more speed. And what does not play well in the modern arena. These are things you can play with when you get your simulations of your circuits up and running. You can extract capacitance. That's one of the tools that you should learn. I hope you get to extraction next Friday in the tutorial. Oh, remember to bring your laptop for that one. And you're going to be using a teaching server. And there's some 45 people still enrolled in the course. So when it comes time to do your projects, you're all going to be fighting against each other to get on the server. Please remember CII 6118, which I have filled and stuffed with extra personalized desktops just for you. Nobody else uses it apparently except my students for this course. And while there's only about 6 or 7 of them in that room, they're resonant cables right on the machine. They're not time sharing with anybody. Response time is incredibly better. So if you're getting a little fed up, you can try to move that token on the screen. Listen, I don't want to move. Because there's 45 other people in this class and 45 in some other class. All fight with you to get to the cycle. Try CII 618, which is open 9 to 5 during the weekday by the technician. And if you promise to buy coffee from one of my graduate students, I might open it for you on the weekend. Treat them nicely. And don't bother them too much, although it is true that sometimes they will come down and help you out if you get stuck, which is another reason why I have that over there next to my graduate students. So when you get really screwed up, you get them home, and there's nobody else around. The graduate students will often over the weekend and other odd hours at night. Not the 9 to 5 on the window. And they may be willing to help out. I don't know where the TAs live for this course. Maybe I know where they are. Maybe they're not sure where. Maybe they don't have it on the side. Okay, so just to remind you again, that's over there. I buy new computers all the time, and I take the next to the last generation and put it out for the students learning this course. So you got some that have like 8 or 16 gigs. Personalized cables right there in the station. You all have good response to that. Hope it's not going to sleep. All right. So what we got so far? What we have at this point is we started out at 0.9 BDD, which is 90%. We're doing a 10%, 90% study actually. When it's all said and done. But we're assuming the input is an absolute perfect snapshot instead of BDD. It's just an artificial thing to make the math simple. And we descended during this first piece to this other voltage, which is BDD minus V threshold N. That's the when we're in position. This was the saturation portion in SAT discharge. Okay. And then we switch over and we're going to run the rest of the way on active. And when we get to, no, we're not going to try to go all the way to 0, that would take infinity. When we get to 0.1 BT, then we will declare victory. Call that distance from there to there is altitude. Where the total fall time is the sum. Right? This one's a little harder to get. A lot more messy math, but it's the same idea. That's why I spent time on just the first part. When we try to get tau F2, it would be minus C sub L divided by beta N BDE minus V threshold in integral from 10th of BDE to BDE minus V threshold in 80% of BDE. This would be this 20% of the BDE body. And then the body of the integrand is going to have that active IDS expression in it, but I've already divided it by BDE minus V threshold N guy out in front. That's going to be important. So there's our V out, and we have V out squared divided by, there's the 2 that we would normally expect to find for the active IDS. And this is in, which is that divided into this. And this thing would normally have that as a multiplier, but I stuck it here, so it's just V out. Okay. Now goes the second piece. And as I say, this is a more awkward piece of math, but I would come up with roughly the same conclusion. I wanted to be another term here for it. Anybody falling behind or need any questions answered? Yes.
On the TF equals tau F1 plus tau 2, wouldn't that include the length of the TF1 twice?
This TF is the whole thing, and there's a TF1 which goes to this point. TF2 is
So
the
it's
second piece.
It's just that.
Yeah, it's just that. So the sum of them, and that's for computing this little piece from here to here. Okay? Yeah. Other questions if you're confused? I want everybody to come out here knowing this stuff. Stone cold. It's nothing in here. It's too hard, is it? It's all just quadratic equation. That's all. Maybe today we'll do a little bit messy. So we're going to start out and look at that. And we've got a term in here which is 1 over, effectively, once I factor it out, V naught times an A V naught plus B. Where the A is 1 over 2 VD minus B threshold N. To the B is minus 1. And then you get that expression there. What I'm trying to do is integrate that. As a method, which you should know about, but may have forgotten. This is why I do this. Here's where some of this calculus gets used. So you don't want to let that calculus fall off the edge of the desk and just fall into the trash can. It should stay up here. Okay. So the method is called partial fraction expansion. Anybody remember that? In which case, we are trying to take something that looks like this and make it look like this. Of course, no certainty that you could do it, except that you could actually show that you could find these coefficients. So can we find A and B? That's the question. And the answer from calculus is yes. What we do is we just multiply these two so we actually get the denominator on the right that we get on the left. This guy has to be multiplied on the top and the bottom by that. And this guy has to be multiplied on the top and the bottom by this. And then you have a over common denominator. In which case, the 1 over V naught times A V naught plus B equals, first of all, there's the A, and now I'll take this guy and put it in there. And there's the B, and I'll put that guy over there. And then there's our V naught, and then A V naught, this is the common, this is an A here. Don't look like it, but it's happens to be the same as the denominator on this side. And the only way that's going to work is if this thing here is 0. Okay? Because we don't have anything over here that has a B naught in it. And okay, so we have to have at least this one here. And then when we get to the other terms, so in order for this to work, we would take all of our B naught terms, this over here and that over there. And since there's no B naught over here, the result has to be 0 as a coefficient of B naught. And what that says is that, let me do that. The continuum of this will be A plus B times B naught plus A will be divided by B naught L plus B. And it's this thing here, we have to make that 0, and then that thing has to be 1 in order to equal what's on the left side of the equation. And then we B naughts. So we get A plus B equals 0. And AB equals 1. And A is equal to 1 over B. And B is then minus A little a, which is equal to minus A over B. So in terms of the original little a's, we have now the big A and B.
And then numerator, is that supposed to be uppercase B?
This has got to be 0.
Up top. You have A plus lowercase b. Where the arrow is.
This was over here, that
The other sheet.
that A and this B here.
You just wrote the lowercase b. That's the other sheet of paper.
That this A and that little B are that.
Where's the button?
Professor, the other sheet of paper.
He's saying the big B.
The other sheet of paper. Not that sheet of paper.
No, the one that's on the
The one that's on the projector.
The one on your
The
right.
one that you're reading.
In the numerator in the first block of parentheses.
Yeah.
Oh. I had to move the two B naught terms together here, right? So somebody caught a boo-boo and gets a brownie point. In the name of the person receiving the brownie, Ian.
Wilson.
F.
Wilson.
Wilson. It was like principals. President of Princeton. Any question? So, you never know. The one I'm going to call ecology technology. Did you know that John McCain, who was presidential candidate, was related to George Washington? He didn't even know that. It was like 11 generations back going forward in a different branch. There was a theorem that a Chinese fellow at Yale wrote. If you take any two people in the world and you go back at least 2,500 years, they will be related. That's about the time of the pyramids. Any two people on the planet, somebody from China, somebody from Ceylon, somebody from Latin America. Any two people, common heritage. We're all together. All right, so Ian gets a brownie point. All right, so where are we? We have, okay, so 1 over B naught times A, B naught plus B, which is our original challenge, is 1 over B naught minus A over B over A B naught plus B, where A again is 1 over 2 BDD minus minus V threshold N. B equals -1. And our integral from B1 to B2, which I'll go over B2 or later, dV naught over B naught times A B naught plus B equals a whole lot of stuff. But mainly, it's this term over here and this one over here. These are natural logs when we do that integral. One over B naught or one over B naught is a natural log. And that is 1 over B, natural log of B naught, minus 1 over B, natural log of A B naught plus B. Evaluating from A1 to B2. Which is equal to minus 1 over B, natural log A B out plus B divided by B out, B1 to B2. And now, for B1 and B2, I'll take to be that 10% number, not the full B, because that would go to infinity. And B2 will be BDB. This is the pink where we track the reverse between that and that. Put all that together, we get tau F2 equals C sub L divided by beta N times VD minus V threshold N times a natural log of this huge bunch of poopycock. I'll show nothing minus VD minus V threshold N divided by 2 VDB minus V threshold N. Squared. That's going to go away there. 0.1 VDD divided by, there's a little messiness here, minus 2.0 minus 0.1 VDD plus 2 V threshold N. All divided by VDD. Minus V threshold N, and the other one of these then cancels with this, leading us to the natural log of 1 over 10 times 1.9 VDB minus 2 V threshold N, all divided by VDD. Which then becomes, after further simplification, multiplying through by the 10, which is basically this 10th thing that was up here, becomes the equal to C sub L divided by beta N VDD minus V threshold N. That's a natural log of 19 VDD minus 20 threshold of the end device divided by VDD. And that's out at 2. We'll be boxing on that. Which, again, we can play games with the definition of this N. Let me rearrange this a little bit so this is equal to C sub L over beta N times VDD times 1 minus V threshold N over VDD times natural log of 19 and divide out the VDD minus 20 times V threshold N over VDD. And that can be put together with the tau one we had earlier, which was tau F. And that becomes 2 C sub L divided by beta N There's the VDD. There's a 1 minus n, which is here. There's the VDD. It's common in both terms. Times, this was a piece we had for the first descent. And this is a new term, which has a 1 in front of it to allow for factoring that 2 over there. 19 minus 20n. Put a really good oxygen on that because that's the final answer. And they both share this common feature that if you want to go fast, you make VDD big. Of course, if you make VDD big, the amount of energy that you're storing on those capacitors before it's all dissipated in transistors is also big. You also have problems with breakdown voltage in the oxides. If an oxide breaks down, I've forgotten what the actual breakdown field strength is, but it's like megavolt per centimeter or something like that, scaled down to the thickness of nanometers. So you have a lot of problems making VDD big if you wanted to do it. And if you did, it would just say you're going to get more power in CMOS. VDD. Okay. Which we can now take that whole equation and simply write as some magical R equivalent times the capacitance of the load. Simple enough. And we've already looked at this, but it turns out if I take, suppose, that I take a typical number that at least with the 5 volt type of thing is reasonable, that n is equal to 0.2, which is typical. And it's hard to keep doing it, because one of the things that's happening now is we try dropping the voltage to get the power down. We got to do other things to speed this stuff up. One of the ideas was using a better oxide so we can boost the currents up and we can drain the current off faster, all the obvious stuff. That we're no longer able to keep squashing the VT down, reaching some fundamental rates on that. Somewhere around a volt, VT is 0.2 of a volt, we're not getting much smaller than that. That's pretty much it for CMOS. But if we can have this, then our equivalent would be 2.92 times 2 divided by beta n VDD, which it turns out is about 6 divided by beta n VDD. Yeah. This is just a numerical insertion into those equations. So, kind of means this almost is what the resistance looks like when you have a lot of nonlinear charge and discharge. So, believe it or not, I've run out of things to say. So have a nice weekend.